So for these example problems, we're going to deal with the secants and the tangents. Again, everyone's favorite. Trig is everyone's favorite, I know. But you can see why there's like not a whole lot of room here to do 5 and 6. These are ones you should be able to handle pretty quickly. If you think about 5, I don't want anyone stressing out over that. The integral of secant squared, you are out of this as quick as you started. You should recognize that secant squared is the derivative of tangent and you're done. Okay, that's what I mean by sometimes they'll throw these almost like curveballs in here, these basic integrals in, just to test the waters. Like, don't go crazy with some of these. Some of them are definitely basic. Now this one, tan squared, is not on my list of basic things. However, I can still handle it very well. It's not on my basic list. I have the integral of tangent alone, which is a complicated integration rule. But if you kind of look at your flow chart for secant and tangent, let me see if this fits into the category. So close your eyes for a second. And let's go up here. If there are no secant factors, right, and the power of tangent is even and positive, convert a tangent squared factor to a secant squared factor. Okay, I can do that. Let me fly back down. They're really just telling you to use those quotient identities. Be efficient and use those quotient identities. So one of your quotient identities involved tangent squared. And if you wiggle it around, tangent squared is the same exact thing as secant squared minus 1. That's a legal trade. You can ditch the tan squared and write it as its Pythagorean identity counterpart. And then, look, this is great because, I mean, these are two separate terms separated by a negative sign. You can handle them separately. Basically, in your brain, I want you to say, like, well, you're going to do the integral of secant squared, and then you're going to integrate 1. Like, you're allowed to do them separately, and now you're really getting somewhere because, well, the integral of secant squared is tangent. Done. The integral of 1 dx is x, and then you're going to slap that plus c for your constant of integration. So these identities, these trig identities, really come in handy at kind of working on these antiderivatives that we're gonna take a look at. Okay. All right. So let's take a look at problem number 7. Certainly more complicated, and they're just trying to kind of get you to be as efficient as possible and see how things are going. With what's happening. So if I take a look at 7, take a look at that flow chart that you have. What I see here is I see the power of tangent as being odd and positive. The power there is 1, right? Like, that's odd and positive. So what their suggestion is in this flow chart is to save a secant tangent factor and kind of rewrite everything in terms of secant. So what does that mean? Let me show you what that means. That means they want you to break apart that secant squared. And when they say save a secant tangent factor, that means I'm going to come at this and say, don't touch this. Whatever you do, don't touch it. Convert everything over to secants. Well, that's all I have left is a secant. So I don't really have anything else to do here. What I'm going to do is sort of take their advice. The reason we're saving this is because that's going to be the derivative of something. What I'm going to do here is, again, a basic u substitution. I'm going to let u equal secant. And its derivative is secant tangent. And I am going to, of course, isolate this for dx equals, because that's what I'm going to do in my u substitution approach. I'm going to come back to this integral and say, okay, well, it's secant that I let equal u. That was what I did here. That's my u. I'm just kind of saving the secant tangent factor over here, but I'm going to replace the dx with its equivalent statement, which is du over secant x tan x. They're trying to give you these ideas and these movements forward of how you can get your answers pretty quickly. Clearly, this was a great idea because these totally cancel each other out and leaves you with an integral that, dare I say it, is pretty easy. You're integrating u du, which we've done several times already in this lesson, which is 1/2 u squared plus c all I have to do is switch back and say, okay, what did I let u equal? Well, I let u equal the secant. Okay. Now that is one way of doing this problem. Interestingly enough, you could do this another way as well. And it's great. It's whatever you see as kind of happening here. Some of you might say, well, I thought there was a different way of doing this. Let me come at it like this. Let's just talk about it for a second. You could definitely approach this in a different way. You could definitely say, you know what? Why don't I let u equal tangent? Because I see its derivative here. This is absolutely going to work. I like questions that have more than one possibility. This is another one of those guys, just like problem number 1. There are 2 paths forward. So let me put the answer to this strategy. If you kind of worked on it while I was yapping and you're like, wait, I don't think I'm right, I got a different answer. You have an equivalent answer. The other answer you can get is this right here. Okay. All right. So let's handle a couple more problems here. Let's handle 8 and 9 in this video. And then, you can take a break and come back to some more stuff. So here we are with 8. Secant to the 4th tan x. Okay. I definitely kind of see a couple of things. Let me take a look at what I've got going on. I've got the power of the secant is even and positive. I have the power of the tangent is odd and positive. And we could see where this will take us. So we can do a couple of different things. But I think I'm going to go with that first one. The power of the secant is even and positive. Save a secant squared factor and convert everything else to tangents. Let's do that. So I'm going to take that advice. The power of the secant is even and positive. I'm going to save a secant squared factor. So you're just breaking apart secant to the 4th like that. This is the one I'm going to save. I'm going to hold on to that. Don't touch that. Leave it there. And then their advice is convert everything else to tangent. So that means I got to ditch this. This has to go. So what's the legal swap for secant squared? Well, the legal swap for secant squared is tan squared plus 1. That's my legal identity, trig identity that I can employ there. Now remember, I'm leaving the secant squared off to the side because I'm supposed to save that. The reason I'm going to save that is because, well, I'm going to let u equal tangent. I'm doing a basic u substitution. The derivative of tangent is secant squared. I'm going to do my follow through that I do on any u substitution problem, and I'm going to reimagine this integral. Again, I'm supposed to save that secant squared, but anywhere I have a tangent, I'm going to replace it with u. I've got u squared plus 1 and an extra u. In place of dx, I'm writing du over secant squared. That right there is the reason that they told you, hey, it's probably a good idea to save one of those secant squareds because that's exactly what's going to wash out in your replacement for dx. So this is great. You've got an integral that's definitely doable now, right? I basically just have u squared plus 1 times u. I'm going to just carry that u in. That is a basic integral right there, just power rule, right? So I'm going to come up with an antiderivative. That's 1/4 u to the 4th plus 1/2 u squared plus a c. Of course, I can't answer my question like this. I have to report back into functions of x because that's what I was presented with. So I will do that here. I'm going to say, do I have room? Put up a minute. Not moving. There we go. 1/4 tan x to the 4th. And again, you can write it like this with parentheses, or you could put, instead of doing that with the tan squared, you can do that. It doesn't matter to me. However you want to write it is fine. Okay, and there's lots of like interesting things that you can do here as well that would also work out. There's lots of different paths that you can go with. This is just one idea in this whole section. The textbook is just trying to give you like a path forward on good choices that get you the answer really quickly. Okay. So let's take a look at problem number 9. And then we'll come at some other problems. So here I have the tangent is odd and positive, right? So if that's the case, they're telling me to save a secant tangent factor, and we'll see where we go from there. So I'm going to break this up. I am going to try to save a secant tangent factor. So if I take one tangent and kind of hang it off to the side, that means I've got tangent squared here. That's just a reimagining how this thing looks. And so I'm going to save this. I want to make sure that I don't do anything. I'm supposed to save this off to the side and just deal with this. I'm supposed to convert everything over to secants. No problem. That means I've got to get this tan squared to go away. And the equivalent for tan squared is secant squared minus 1. Okay. So I'm going to kind of rewrite everything that's going on in my integral. And I'm going to get in here with a u substitution. Whatever you converted everything to, that's basically your u substitution. You're going to let u equal secant. Now, the derivative of secant just happens to be secant tangent, which was the whole point of you saving that secant tangent factor in the very beginning. Okay, so I'm going to come at this integral and say, okay, well, I'm not messing with that secant tangent. They told me to save that off to the side. I'm going to do that. And anytime I see a secant, that's going to be u. My follow-through for dx is du over secant x tan x, which is exactly that perfect thing that you needed to happen. So all of this entire section here is getting these crazy integrands with trig functions down to something that's actually really nice, integrating u squared minus 1 du. You can all do that in your sleep. You're sort of getting rid of the trig function so that you can really pay attention to your integration rules. So what I'm going to do here is just switch back to secant. Okay, that's what I let u equal. And we're good. Okay, so I'll come at the next questions in the next video.